Okay, I think we can start. Welcome everyone. So today we are very happy to welcome Evan Anders. And so he completed his PhD at the University of Boulder, of Colorado in Boulder. And he did that a few months after the start of the pandemic. So that must have been not easy.
Yeah, it was an experience.
Yes, and so he stayed a while, for a few months in Boulder, but then he moved to Lake Michigan to start a postdoc, but he's still now at Northwestern University. His expertise is computational fluid dynamics, and that will also be the main meat of his topic today. So please, Evan, you have the floor.
All right, thank you. And thanks everybody for having me here. It's been lovely visiting Leuven this week. You might notice that the original title that got sent around is in tiny words under the main slide title. I'm gonna try to get to that also, but those results are like newer and fresher, and I didn't feel like I could talk for 45 minutes. So let's start off with stuff that I do feel like I can talk about for a while. To give some context, because you know, it's nice to not jump right into fluid dynamics. So here's the HR diagram. A lot of us think about stars. This is from Gaia. So we've got luminosity on the y-axis, temperature on the x-axis. The color tells you how many stars there are at that given color and luminosity. And the big stripe down the middle is the main sequence with the fully convective M dwarfs, et cetera, on the lower right side. Stars like the sun kind of in the middle, and then massive stars up at the upper left. And there's other features on here, white dwarfs at the bottom left, evolved giants in the upper right. But basically everything I'm gonna be talking about in this talk is these stars up here, massive stars on the main sequence. I'm like a hydro modeler, so these are all gonna be at the 0 age main sequence. They just started. So, but they're massive stars, they have core convection zones. And these stars matter in a lot of different fields of astrophysics. I'll just give a couple of examples really quick. So here's some kind of beautiful simulations of the winds of a massive star. So what you can see here is that there's a massive star shooting out ionizing radiation and winds in the center of the simulation. There's some sort of interstellar medium around that star, and the production from the star is sweeping away the interstellar medium and causing turbulence in it. And both of these things are important. So the sweeping away of things and the turbulence could all lead to have different consequences for star formation and things like that. And also, these are the stars that turn into black holes and neutron stars, which is kind of an exciting thing nowadays, now that gravitational waves and LIGO and LISA have, LIGO and LISA have started observing gravitational waves. We'd like to know what types of stars with initial masses on the x-axis and initial metallicities on the y-axis, what do they turn into at the end of their lives? This is kind of one of the big questions that I tried to contribute in a small way to. By the way, when I'm like breathing, I feel like the mic is picking that up. Is that happening, or am I just, okay, great. Cool. So when we look inside of these stars, this is sort of what we think the basic structure of them looks like. So there's a core convection zone, that's the blue shaded part in the middle. There's a iron convection zone or other ionizing convection zones close to the surface, that's the blue stripe near the surface. And in the rest of the star is a radiative zone filled with gravity waves. And the first part of this talk, I'm gonna talk about the boundary of that blue zone in the center. It's not actually clear where that boundary should be. Maybe it's a bit bigger, maybe it's a bit unclear. Okay, so there's a few observations that at least suggest that massive stars should have larger convective cores than our standard 1D stellar models produce. Keep in mind, I'm not an observer, so this is all my impression of them. And if I misrepresent anybody's results, please stop me and tell me, because I would love to learn. Okay, so here's a spectroscopic HR diagram. Kind of like the Gaia HR diagram, the colors tell you basically how many stars there are at that luminosity and temperature. And this is a zoom in on the upper main sequence. So the left side of this sort of dense region is the 0-age main sequence, or the ZAMS. The right side of the dense region of stars is the terminal age main sequence, or the TAMS. And if you kind of just draw on lines by eye, you get those red lines that you see up there on the plot. But if you run a stellar model or a grid of stellar models with a fixed amount of mixing outside of the convective core, you get tracks that look like this. And so they start on the 0-age main sequence very nicely in terms of the fact that they do line up with that leftward line. But they have this hook at the end of the main sequence, and that hook looks fine, maybe at the bottom of the right red line, but then it kind of cuts up and to the left compared to the observed terminal age main sequence. So yeah, from our models, we might expect that that's what the TAM should be. That's not what's observed. If you then run a bunch of grids with different amounts of mixing, if you increase the mixing, you can push the end of the main sequence out to the right. And each of these lines is a different set fixed amount of mixing used in the models. And so you can see that you need a different line at the bottom of this plot than you need at the top of this plot, which is to say that mixing is a function of stellar mass. So that's unfortunate. You, Cole, work on these types of stars, so I'm probably going to say something you disagree with. Tell me if I do. So basically, eclipsing binaries are great because they're binary stars that pass in front of each other and block some of the light from each other. And this means that we can precisely measure things about them, like the mass, radius, and luminosity. Is that all true so far? Great, OK. So Clarion and Taurus measured a bunch of these and made some questionable choices when they made some models, like they didn't make the metallicities all the same. OK, but they found that in order to produce the sample of binaries that they saw, they needed a mass-dependent mixing that looks like this. So the dots are the different stars in the binaries. The y-axis is exponential overshoot mixing, whatever. Basically, up higher on the plot means more mixing in the model. And so you can see that stars with masses from 1 to 2 solar masses, there's like a really steep trend with stellar mass, where you need more mixing at higher mass. And then maybe there's a plateau, although there's some pretty big error bars on this. And this all sort of sucks. So we don't want to have this like mass-dependent mixing that we have to calibrate based off of observations where we don't necessarily trust the methods that were used to calibrate them. What we want is something that comes out of the physics self-consistently. And this Kaiser 2020 paper, they basically just took the different mixing parameters you can put into a stellar structure code and turned the knobs to all the values that people use in the literature, and the range of values used. You can, for the same stellar mass, change the stellar lifetime by something like 30%, and you can change the core mass at the end of the main sequence by like 70%. So this has huge consequences for the remnants that come out of our models. And Mai Peterson had this great paper in Nature Astronomy a couple years ago with this nice picture of various light curves from various stars. And you can see that there's these oscillations in the stars. And if you take the Fourier transform of those, you get these nice frequency spectra here in color with really sharp peaks. And these peaks correspond to standing G modes in the stars. And you can use those G modes, you can make a MESA model or a stellar model that has the same characteristic frequencies to learn something about the insides of these stars. And what Mai found from this study, at least my like 0th order theorist interpretation, is that you can make models with boundary mixing that looks like this, a kind of standard overshoot where it falls off with distance. Or you can make models with mixing that looks like this, where the mixing doesn't fall off with distance. It just kind of keeps going past the boundary of the convective core. And stars like that one more. And that's kind of curious. And we wanted to figure out why this was the case. OK. So before I get too much into the actual experiments we did. Oh yeah, this part. Forgot about like 5 slides. Okay, yeah, so there's a few different processes that I like to talk about from like a fluid dynamics perspective when I talk about convective boundary mixing. So it's not just profiles, there's actually like things that are happening in the fluid that cause this mixing to occur. I meant to put a slide in here saying this, but Maya and I just wrote a review paper that appeared on arXiv like last week. I encourage you to check it out for more details, but this is gonna be like a really quick summary. So if we now zoom in right on the boundary of this core convection zone, you might have a little setup that looks like this. The white region here is a convection zone. The purple region is the stable radiative zone. And you can imagine you have this little blob, this convective parcel, traveling upwards out of the convective zone. It overshoots into the radiative zone until its kinetic energy is fully converted into potential energy and it comes to rest. And then it kind of blobs its way back down or dissipates or something happens. So this process where you have like a convective blob, it passes over the boundary and then it comes back down, is called convective overshoot. So this is not, when I talk about convective overshoot, like a general process that could mean anything. I'm specifically referring to this like thing goes up and kinetic energy turns into potential energy process. Okay, so this has been seen in simulations as long as they have been run. Here's some nice simulations. I think these are 2-dimensional by Tammy Rogers back from getting close to 20 years ago now. And so there's 2 different simulations here. The top of the simulation is an unstable region. The bottom is a stable region. I think the initial convective boundary is the black horizontal line, and the field you're seeing is vorticity. And you can see that there's one of these has a thing that says S equals 3, and another one has a thing that says S equals 510. And yeah, so you can see there's some different dynamics between S equals 3 and S equals 10. And basically, these S values are the relative stability or the stiffness of the interface of the convective boundary. So when S is small, that means that the unstable convective motions are about of the same instability as the stable region is stable. So they can shoot way past that boundary. They don't get damped very fast. On the other hand, when you have a high stiffness, that means the stable region is very, very stable compared to your convective motions. So you don't get much overshoot. We think stars are mostly in the right regime, not super much in the left regime, except for very high Mach number convection at like the solar surface and maybe those surface convection zones I mentioned earlier. Okay. A second process a lot of people have thought about a lot is this process of entrainment. So here, same picture. Now you have some convective plumes. These shoot up into the stable region, they scrape material away from the stable region, they drag it back down into the convection zone. It mixes, this happens a lot, and over time, maybe the convective boundary moves upwards, or at least that stable region gets emptied out of some of that stabilizing fluid. So this, I think, has been studied in like the geophysical context since the 60s, including like people just like set up tanks of salt water in labs and like heated it and just saw this process happen. But in the astrophysical context, this Meekin and Arnett paper from 2007 were the first people to really talk about it. And so what they did is they ran simulations of, I think, oxygen shell burning. And here you're seeing the gradient of the oxygen concentration with radius. That's what the color is. And so the places that are like really sharp white points are where there's a really large gradient, which is to say that's the boundary of the convective region. And you can see that there's like a lot of mixing, and especially the top boundary moves upwards over time. So this boundary is being entrained. The convection is pulling the stable fluid from above it into the convection zone and mixing it. And so this boundary is moving over time. Okay, and then the third process I'm going to talk about is penetrative convection. I'm not actually going to describe it yet because I'm going to spend like 20 minutes doing that, so let's not. Okay. But basically, the idea is that in addition to your convection zone and your radiative zone, you have a well-mixed region outside of what you would expect the convection zone to be. Okay, so this is what the transition I was expecting earlier was. So I used the Daedalus code. This is a code that you can use to solve arbitrary partial differential equations using spectral methods. So as an example, let's say you wanted to solve this system of equations. You wouldn't do like from Daedalus import Boussinesq convection equations. You could actually write these equations out yourself in Daedalus to build the solvers and stuff to solve your science. So here, these equations are just the incompressible equation, the momentum equation, and the energy equation under the Boussinesq approximation with an internal heating source. So kind of a really simple model of like a stellar core, for example. And if you wanted to put these into a Daedalus problem and solve a simulation, this is actually what the code would look like in Python and Daedalus. It would then parse it and build wrappers and matrices and things in C to solve these equations for you. But you can see, for example, the div u equation becomes div u plus a tau thing that we use to enforce boundary conditions. So it's nice, it's easy to work with. Once you get like really deep into the matrix of Daedalus, you learn a lot of weird things. I've been using it for way too long. But like to get an experiment up and running, it's fast, it's easy to add new physics, and it's really nice. So highly recommend checking out. And if you're interested, I'm happy to talk with you and get you started. Okay, so we used this Daedalus code to run some experiments where we were trying to understand convective boundary mixing. And we started off with, basic convection in a box. So here on the left-hand panel, we have vertical velocity. And on the right-hand panel, we have temperature perturbations compared to the background. So the left panel, orange stuff is upflows, purple stuff is downflows. In the right panel, red spots are hot spots, blue spots are cold spots. And then we added a convective boundary with like a height-varying radiative conductivity to these. We ran them for a really long time, and we saw this. So the dashed line is where we expected the convective boundary to be. This is the Schwarzschild boundary. And then there's a solid line above that. That's where we actually measured the convection zone to stop. So that's like where the velocities vanished, for example. So you can see if you look at the velocity field on the left, you can't really tell a difference between the stuff below the dashed line and the stuff above the dashed line. The convective motions just continue above it. They don't really care that we thought the boundary should be at that dashed line. But if you look at the temperature perturbations, there are some differences that you can see between the nominal convection zone at the bottom and the penetration zone in the middle. So there's this kind of big hot upflow at the bottom left of the simulation. You can see that at the dashed line, that hot red perturbation turns into a cold perturbation, which is to say that there's a cooling process that happens in this penetration zone. Hopefully we'll get to why that happens. And then the same thing happens for downflows. They actually start off hot, and they cool and turn into what you would expect downflows to be. At the top of the simulation domain, there's a bunch of internal gravity waves running around that are excited by convection. We may or may not get to talk about those at the end. Okay, so what causes this extra mixed layer? Well, if we look at the grads, the stability gradients, etc., you might have a simple model that looks like this in one of these simulations or in a star. So grad add is the adiabatic gradient. That's the maximum gradient that is allowed to be achieved. It's as steep as the gradients are allowed to go. And then grad rad is how steep the gradient would want to be if radiation were carrying all the flux. So you can see in the bottom half here is a convection zone, because grad rad is above grad add. It's trying to be too steep. At the right, it's a radiative zone because it's below. And so in like a stellar model, or most simulations, we would expect the actual grad to do something like this, follow the adiabatic in the convection zone, follow the radiative part above. So yeah, adiabatic there, it's subadiabatic in the radiative zone. So what we see in our simulation is these penetration zones. These were described by Zahn in '91, also by Ian Roxburgh before that, also by Shaviv and Salpeter before that. Anyways, they've been thought about for a long time. There's been some various descriptions of them. But the idea is that now you have this extra zone where convection is managing to push grad actual above grad rad up to the adiabatic value. And I've been drawing these nice schematics that kind of show what these look like. But when we actually measure the profiles from our simulation, they actually look like that schematic, right? So grad now is the purple line, the nominal Schwarzschild boundary is the vertical dashed line, the grad actual is the green line, and you can see that it follows the adiabatic value well beyond the Schwarzschild boundary, and then it falls off. Okay, so what are the energetic consequences of having this zone? So instead of looking at the grads, let's now look at the stellar luminosity. So we know that the star has to carry its luminosity outwards if it's in thermal equilibrium. So if we have a radiative flux that looks something like this is before we have the penetration zone, by the way. This is just like standard modeling. Then we have to have a convective luminosity that looks like this. And so those two things add up together to equal the total luminosity, and we're in energy equilibrium, and everything is happy. But if we now add this extra zone, maybe we're a little less happy. So we've mixed the temperature gradient to something steeper than it wanted to be before, right? And so that means that the radiative flux is carrying something in excess of the total flux. And so the convection has to compensate. So it has to become negative. It has to start carrying flux the wrong direction in order to make this zone energetically work out. And this is a little concerning, but it is actually something we can see with our own eyes in the simulations, so that's a little more comforting. So the convective flux is basically the correlation of the velocity and the temperature perturbations. So if you have hot stuff going up, it's positive. If you carry cold stuff down, that's still positive. But if you carry hot stuff down or cold stuff up, that's going to be a problem, or it's going to be a negative convective flux. So here you can see in the nominal convection zone, let's look at that bottom left plume again. It's traveling upwards at the bottom left, and it is hot in the bottom left, so that's positive flux in the convection zone, yay. But the vertical velocity doesn't change sign in the penetration zone, but the temperature perturbation does, so now we have cold stuff going up, negative flux. Okay, so we see this thing happening. We expect it to happen just based on the grads, so this is maybe comforting. But as far as like, why is this zone here? How does it stop growing, etc., we have to do a little more math. Okay, so if you have a kinetic energy equation, this is just like from the equation of motion, you get something that looks like this. Change in time of kinetic energy, divergence of various fluxes, and then there's a buoyancy term associated with convection creating kinetic energy, and a dissipation term associated with like the turbulent cascade taking energy out of the system. So if you take a volume average of this equation, and then you assume you're in a steady state, which stellar convection normally in a steady state, we can get rid of that time derivative term. And if you assume that the velocities are basically 0 outside of the convection zone, you can also get rid of that flux term because they all depend on the velocities, and that is a surface integral. So what we're left with is basically the kinetic energy that's being generated by the convection has to go into the turbulent cascade and get balanced out. And this buoyancy term, like I said, is just the correlation of the velocity and the temperature fluctuations, which ends up being the convective luminosity in spherical geometry. And this thing is positive, as we saw in the convection zone, and it's negative in that penetration zone. So if we break apart our integrals to have pieces in the convection zone and pieces in the penetration zone, and we rearrange this equation so that all the terms are positive, we basically have an engine of convection creating kinetic energy on the left-hand side, and both the turbulent cascade and this weird penetration zone getting rid of kinetic energy on the right-hand side. And I like pi, so I just think of it like this. You've got your whole pie of kinetic energy, and you've got two sources or sinks to get rid of it. One of them is the dissipation, and the other is this new zone that we have. So the buoyancy terms, they're just given by luminosities, so you can just get those straight from stellar structure. That's great. We actually use the only thing we're using these 3D simulations for really is to calibrate how much is going into the dissipation of the turbulent cascade and how much we have left to build this penetration zone. And so what we found was this. Yeah, basically, 86% or so of the kinetic energy that was produced goes into the cascade, goes down to small scales, goes away. But that still leaves 14% to create this extra zone. And that's not zero. So you do get some extra zone where there's this negative luminosity getting rid of some of the excess kinetic energy being generated in that zone. And so this is why I'm here. I'm collaborating with Cole and Matthias. And we're trying to put this self-consistently into MESA and figure out like how does this look as a function of stellar mass and as a function of age and et cetera. So here we've basically taken this equation and calculated how big this penetration zone should be as a function of age. Age is in color. Yellow is the end of the main sequence, purple is the beginning, so it goes from purple to yellow in time. And stellar mass on the x-axis. And so you can see right when the convective core is appearing at low stellar mass, you get a really small zone. It increases with mass pretty monotonically. There's maybe a little bump around 2.5-ish masses. Okay, and so if you add those eclipsing binary dots from Clarion Taurus and all of the previous models from before, they're all kind of clustered towards low mass, so look at the inset maybe instead of the whole thing. So you can see that we get a slight underestimate, but we also reproduce the trend that they see where it falls off at low mass. And this calibration was done using like the bare minimum of the physics, so incompressible equations, Cartesian box. So there are places where we can improve this to create a better calibration, but it still gives us a self-consistent zone that grows with mass, and we don't have any free knobs here, right? We don't have like FOV to change, we don't have alpha OV to change, we just have an excess zone above our convection zone that comes out of the physics, comes out of the models. So stay tuned. We're going to write a paper on this hopefully in the next few weeks, and that'll be showing up. How much more time do I have? 15 minutes? Okay. Are there questions on this before I move on to something kind of completely different? I saw a hand for a second.
Interest, right? It was not really clear because 40 stellar masses is quite high. So these stars, of course, become very radiation dominated.
Yep.
At that end. So it wasn't clear to me how you handled that in your incompressible formalism, both in the momentum and in the energy term, because I know since we're doing 3D envelope and atmosphere and wind models, there it's a mess. So I don't know here, just out of curiosity, how you're dealing with those terms.
Yeah, so the question is, how do we deal with radiation pressure domination at high stellar mass? And the answer is, we don't yet. But I'm currently working on getting those equations up and running. And the reason we haven't included it is because the constraint that I'm talking about here, these source terms don't really depend very much on the equation of state. So Roxburgh's integral constraint and also the PDV, well, I guess PDV could depend on this, so that's where things could get tricky. Yeah, exactly. But the PDB is balanced out by, actually it doesn't actually matter for this, it doesn't enter. What does matter is the convective luminosity, the temperature gradient, the temperature, and the dissipation. And so I do want to see how that matters, and I think within a year's time I'll have a better answer for you. But right now we don't handle it. Good question. Yeah. Cool.
Question for me, Evan.
Yeah, Don.
First comment, everyone should read Evan's review paper. It's truly excellent, so just emphasizing that.
Thanks for organizing it.
You're welcome. Question, so in your previous diagram, so presumably here, am I understanding correctly that the FOV is 0? This is only the penetration zone and there's no boundary mixing layer on top of that?
Matthias and Cole, is that right? Yes, okay, yes, no.
Okay. Yeah, that's what I want to know. So for this, it's off, right?
Yep.
Okay, so I'm a little surprised, but I guess in a good way and a bad way, that there's not that much difference between the age then? Do we have an explanation for that?
I think so. So basically, the main thing I think that really changes with age, especially for these low mass stars, is the composition gradients outside of the core. And the penetration scheme and convection in general don't really care too much about that. They will just entrain it away. So we've assumed this just depends on grad add and grad rad, basically, not the grad mu. Yeah.
Okay.
Does that answer your question at all, or is it?
Yes, yeah,
Okay.
I guess there's a compensation between these things.
Yeah.
Just a tip, there's also that 25 solar mass Beta Cephei star, which I think will fit perfectly on those lines. So you should include that on your plot. But that might be coincidence, but you should do that.
We should. Cole, do you know which star that is?
Anyone else have a question? If not, Anders can continue.
Okay. So yeah, now let's move on to something that I'm a much newer hand at. But so, not asteroseismology for the record, I don't do that. But yeah, so the asteroseismology works great for the stars in the instability strip, but Dominic had some cool observations from a few years ago that when you look at hotter, more massive stars that aren't in the instability strip, you see a consistent signal of noise, red noise. And it's a low frequency signal. It's 10 to, or I guess this one is like 1 millimags. Okay, yeah, it's like 1,000 micromags. Okay, so it's like greater than or equal to about 10 micromags, I think. At frequencies less than about an inverse day or maybe a few inverse days. And this is like ubiquitous, right? It's like there were 117 stars in this original sample, and I think 114 of them had this signal. And so this is, what is this? We don't know, and it could be gravity waves, and so now we are all of us theorists are excited about like how do gravity waves from core convection look when they get to the surface of a star. So our approach to figuring out if this signal is waves comes in two parts. We think we need two pieces. We first need to know what are the characteristics of the waves excited by core convection, and how do they vary with frequency and with spherical harmonic degree. And we need to know how do these travel from the core to the surface of the star. So to do that, we assume that the waves are linear, and we use a normal mode decomposition. So what I mean by that is that we assume that the observed luminosity variations at the surface of the star can be expressed as a sum over all of the eigenvalues and eigenfunctions that come out of, say, gyre. And then these are scaled by an amplitude which we get from the convective simulations. So we kind of think of this as like a filter, where the convection is generating waves like, you know, a speaker or something generates music. This gets passed through a filter, or music, sound waves bounce off of the walls in a room with bad acoustics, and then you observe something that looks a bit different at the surface. So then the big question is, okay, that's a nice model, but does this work? So as a really simple test of this equation at the top of the slide, I just have a 1D atmosphere. It's a atmosphere that permits gravity waves, so it's a stable stratification. And in the top panels, I'm going to show forcing. So basically, I'm just exciting waves in these atmospheres at 3 different frequencies. And in the bottom panels, I'm showing the response of the atmosphere to that forcing. So the 3 different frequencies are a low frequency at the left, non-resonant but like moderate frequency in the middle, and then a resonant frequency on the right side. And when I say resonant, I mean like I'm forcing at one of the eigenfunctions or eigenfrequencies of the atmosphere. And so what you can see is that for the resonant mode, this energy just gets pumped into the wave and the amplitude increases over time. Great. For the non-resonant mode, but it's still at a moderate frequency, you see that there's like a combination of multiple different modes that build up to form some sort of signal, but it doesn't really build up to a huge amplitude. And then for a damped mode at low frequency, there's not much of a response. And you might not be able to see it super well, but there's a black line and an orange line on the bottom panel. So the black line comes from just running a simulation where we run this forcing and we measure what the velocity field is. And the yellow line comes from the equation at the top of this slide. And they lie right on top of each other throughout the full evolution. So at least in a simple model, this works very well. Okay. So now let's do a less simple model. So here's the 2 types of simulations that we run. These are based on a 15 solar mass LMC model, zero-age main sequence from MESA. And we run 2 types of simulations. One we call wave propagation simulations. Those are on the left side. And one we call wave generation simulations. Those are it's the same simulations shown in the middle panel and the right panel. Okay, so the wave propagation simulation is basically the one where we test out this filter and how the waves propagate and bounce throughout the star. Whereas the wave generation simulations in the middle and the right, those are the ones where we're just looking at what is the sound of the convection and what is the spectrum of the waves generated by the convection. So what are you looking at here? There's a lot going on. So the left panel, you're looking at the temperature perturbations away from the background of the wave propagation simulation. So this simulation spans 93% of the star by radius. I think it's like 99.99925% by mass, but we like thinking in radius because you can see there's still quite a bit of the star not there. And so you can see the waves have temperature perturbations of like a Kelvin. The core convection has temperature perturbations of like 30 Kelvin. Then we zoom in, and in the wave generation simulation, this is like a recording booth for gravity waves. So you can see there's a big convective dipole in the core. The middle panel, we're looking at the radial velocity, and we're normalizing by the standard deviation of the radial velocity at all radial values. And the reason we're doing that is so that you can see both the waves and the convection. And you can see there's like a little grayed region on the outside of that simulation. That's because there's a damping layer there where the waves are being damped. So they're being generated by the core convection zone, they're traveling out, and they're being damped near the surface. And this lets us measure what is the sound of the waves without reflections messing with things. And then in the right panel, we just zoom in on the core convection zone. We show the velocity not normalized by radius, and so you can see the core convection, but you can't see the waves because they have much lower amplitudes than the core convective velocities. Okay, so the first thing we want to measure is the convective forcing. What is the amplitude that goes into this equation? And looks something like this. So we're measuring the wave luminosity. The wave luminosity is just the luminosity being carried by the waves. And if you have driving at the bottom and damping at the top, and you measure the luminosity anywhere in the middle, it should be constant at any radii. Indeed, it is constant with radii. Okay, so this is the spectrum that we get. We get, on the left, the spectrum of the wave luminosity with frequency. We see it decreases sharply with frequency. And this means that convection excites waves more effectively at low frequency than at high frequency. At a fixed spherical harmonic degree, this is the dipole mode. On the right panel, we see that convection excites more effectively at small scales, which is to say high spherical harmonic degree, than at large scales. And these two scalings come out of Goldrick and Kumar, 1990, and Daniel Lekone and Elliot Quadrat's 2013 work. Basically, you assume that there's a turbulent cascade and the turbulent eddies stir waves, and you get these scalings. And we see those scalings. You can see that there's a bunch of different colored lines here. So the lighter pink line is a more laminar simulation, and then as the lines get darker, we increase the turbulence up to the level of the turbulence seen here. So this one is our most turbulent simulation, and that's the darkest line here. And so what we see is that once we get to fairly high resolution, fairly high turbulence, like the Reynolds number 3000 simulation, we don't really see much more variation with these spectra. And this works well for these frequencies and this L, and it works well for at least, well, many frequencies, but here's the first 4 spherical harmonic degrees and 4 various frequencies. So yeah, that's what the amplitude of the waves looks like, driven by convection. I'm not going to spend too much time on this section, because this is like 10 pages of math to get a result. So basically, this is what the filter looks like. So you have the resonances, where if you dump energy into them, you just keep on getting more and more and more power. You have intermediate frequencies, where you can dump energy into it, and you'll get a response from a bunch of different modes, and it's not huge, and it's not tiny. And then you have strongly damped modes. And then you can see there's a weird artifact on the left side. This is because we only expand out to about 100 or so eigenvalues, and we don't expand out to infinite eigenvalues. And so numerical errors in our technique end up in compiling there when we calculate dual basis to the eigenfunctions. Okay, so now we're going to put it all together. So we have this simulation which measures 93% of the stellar radius. We measure what the surface perturbations of that simulation look like, and that's the black line. And then we also get all of the eigenfunctions and eigenfrequencies of this simulation, build the transfer function from the previous slide, and we run the wave luminosity from a few slides ago through that, and that gives you the orange line. And they agree nicely, and we are excited. You will notice there's that weird little tail on the left side where we lose accuracy because we aren't expanding to infinite modes. But there's basically 3 features in this spectrum. There's radiative damping coming from the low frequency modes, or yeah, because those the low frequency modes are damped heavily. There's this slope where basically convection excites at low frequencies close to the convective frequency better than high frequencies. And then there's resonant peaks. And this is great. It works for our simulation. And so now that it works for our simulation, we want to be able to say something about stars. So I built a transfer function based on the eigenfunctions and eigenfrequencies of my simulation for this plot. I'm now going to build a separate transfer function based on the full mesostellar model and gyre modes, and then pass the convective wave luminosity from our simulations through that different transfer function. Yeah, that's what this is. We're also accounting for a few things that we didn't account for in our simulations. And you observe at high L's, you have bright spots and dim spots that cancel out more and more as you go to high L's, so we're accounting for that. Limb darkening, so most of what you actually end up observing is like L equals 1, followed by L equals 2 and L equals 4, and then a little at L equals 3, and then higher L's are small, but they're all included here. So we did this for 3 stars. The 15 solar mass LMC star was kind of our fiducial one, and that's because we don't expect surface convection for that star. So that won't muddy the results if we get to observe them. And then we also ran a 3 and 40 solar mass galactic solar metallicity star. And we wanted to compare a few of the observed red noise features. So those stars appear here on the spectroscopic HR diagram as circles. The mist grids are the grids I'm using for the background grids here, and they're colored, the pink to darker pink is colored with distance from the mist SAMs in this plane. So when we look at our stellar models, and these are hot results, so I just submitted them a few days ago, and I'm like, but please don't share until this is on archive, is basically what I'm trying to say. So here's what we see. We see fairly low magnitudes. The 40 solar mass star is a little less than a micromag, and the lower mass stars are even smaller than that. And we see the three features here: radiative damping, which is fairly large at the surfaces of these stars, modes to the right side, and then kind of an intermediate peak. And that slope comes from the convective driving as you go to high frequency. And yeah, they're pretty different in amplitude from the red noise. And I'm really bummed out by this because I wanted to use the red noise to learn about core convection, and I was really hoping that these signals would look the same. But I think we have a pipeline here that we can use to describe waves and convective excitation in stars. And so I think that we hopefully can start comparing simulations and some observations of waves and learn something about the amplitudes of waves and observations and simulations. I just want to take a few minutes really quickly to advertise some other great people who I get to work with, who don't get the pleasure to join me on all of these great trips. So Emma Kaufman is a graduate student at Northwestern. These are old slides. Emma is not visiting with me. So Emma works on gravity waves and stars, is starting to work on gravity waves and stars, and has a paper out on the Prendergast magnetic field, which is visualized here. This is a magnetic field which is thought to be stable on stellar lifetimes, and Emma found out that jokes it's not, and that is a huge bummer because she was trying to study how waves and gravity waves and magnetic fields interact, and instead all she got to study was that this magnetic field grows. So hopefully she actually gets to work on waves soon. Liam's another student at Northwestern doing some really cool work. He is like solidly an applied mathematician, and so he's working on adjoint looping mechanisms where basically you are trying to find optimal states of a system, like a dynamo or something like that, and so you're just like iterating your initial conditions through this diagram, which he says is adjoint looping, and I trust him, I guess. I trust him, he is good. So basically what he has done is that he's taken old techniques, which are the solid lines here, and this is a plot of error versus iteration in adjoint looping, and he's modified them to be better to the dashed lines, so you get much less error in like your objectives and the things you're trying to solve for. So that's cool. Liam's doing great there. Whitney Powers is another great graduate student working at CU Boulder. She's working on fully compressible stratified convection, finishing up this paper on internally heated convection, and is soon going to be thinking about how rotation affects convection. Amy Cresswell has worked on how strong magnetic fields interact with convection, also at CU Boulder, and is next thinking about how thermohalide mixing in RGB stars can be modeled, and specifically, how do we model the progression of a thermohalide front as it goes from where it appears to connecting with the convection zone. And finally, Rafa Fuentes, postdoc at CU Boulder, has done a lot of great work on entrainment, and he and I are getting together a paper on how rotation and entrainment affect one another. Okay, so 2 things to wrap up. We generally understand this process of convective penetration and convective boundary mixing by this process. We think it's responsible for these expanded cores seen in observations. And we've made these simulations where we think we're the first people to actually be able to predict the amplitude of convectively excited waves, not just the shape. Yeah, we are excited to use this pipeline to hopefully connect with and learn things about observations. So thank you all for your attention and time. Really appreciate being out here.
Thank you very much. Very nice talk. Are there any questions or comments or feedback?
Hey, Pablo Marchán over here. I'm curious, so for all this discussion, what I hear a lot is like there's a camp that says it's gravity waves from the core, and there's another camp which is said it's subsurface convection, which is also a form of convective motion that produces it.
Absolutely.
So I don't know what you can say about that.
Yeah. So I didn't have an opinion until I did this work, but I am associated with the people who are in the camp of it's the surface. And so now that I have seen that my results say that the core generated gravity wave should be small, I think it has to be something else. And the only thing I can think of is surface. But, part of this comes from the fact that the sun, which also has surface convection, has red noise. So like it kind of matches with that intuition. But I can't say that it is surface convection generating this. I can just say I don't think it's this generating it.
Okay, thanks.
Mm-hmm.
Please don't do that, Evan. Go back to that beautiful plot. Okay. I have one pertinent question for the left figure.
That one.
Is that what you have transferred to the inertial frame of an observer? Because typically rotation frequencies are between 0.1 and 1 per day for these stars, and you have to make that shift in your lower graph. And then your bump disappears. And that's what we see. I have been telling that to some people since many, many years. You have to include rotation, whether you like it or not. Not in your simulation, but in the projection to the line of sight.
Okay, so these don't include rotation at all. We have included one simulation with rotation, but we haven't figured out how to include that in the transfer function, and we should talk, because I don't know about that.
Because I don't see a contradiction.
Okay. Yeah, so I will just say on the rotation note, we did run one rotating simulation. We didn't run a very rapid rotator. So this has a rotation period of about 10 days. When you run really rapid rotators, you run into trouble with the convection because simulations have more diffusivity than nature. Rotation increases the diffusivity where convection onsets, and so you can actually get laminar flows even though you think you're looking at a star. So this is about as rapid as we can rotate while still trusting our convection. And we do find it boosts the wave luminosity a bit, like a factor of 10, which results in a square root of 10 boost to the amplitude. So it's possible that rapid rotators could have a more visible signal from rotational boosting. But yeah, we don't know how to do the spreading. Yeah. I have never heard of this, so no. Okay, so the radiative bump gets spread. That gets spread out to low frequency? Great, okay, cool. I would be happy for that to happen. Yeah. Yeah, they're just Lorentzian fits. Yeah. But I assume that's partially what the data has available, right, Dominic? It's just like you can't go to infinitely long. Okay. Okay. Oh, do they? Okay. Okay, because we didn't have access to those. Yeah, I should have asked. Okay. Well, I looked at the appendices and didn't see stuff go down. Cool. Okay.
Yeah, sorry to launch in. It will be a little bit either or, because my question, perhaps not unsurprisingly, was more or less the same as Pablo already asked, but I thought I'll take, since you're here, the case to follow up a little bit on that.
Yeah.
So to me, always this. I mean, these are beautiful models, really, really nice. But the thing with the surface in massive stars, right? I mean, yeah, you mentioned the subsurface convection zone. It's pretty violent when you go up in mass, and it's not just. I mean, it penetrates upwards, and then of course the surface itself is also outflowing because of these nice winds that you shed. So in general, we expect a lot of turbulence out there. So it's never really been clear to me how, in a massive star, this type of signal wouldn't just, how it could survive, how it wouldn't just be washed away by those zones. So I don't know if you have any opinion, because yeah, you model most of the star in mass, right? But I guess you're deeper than than that layer, right? You're not at 200,000 Kelvin or something like that.
Right. So we don't expect this model here, specifically the 15 solar mass one, to have a subsurface convection zone. LMC metallicities and SMC metallicities, you can get to low enough metallicity where you get stabilization. But generally speaking, I agree that the subsurface convection zone is going to be high Mach number turbulent. It's going to produce big motions. And I think Will Schultz had a paper 1 or 2 years ago where he looked at some simulations in Athena, and they were fairly large amplitude noise-like signals.
And Will's models actually underestimate the velocities because he doesn't model the wind, right? He does it with the opal opacities, so basically the same opacities as you do. So you really need to do a combined model, like we're working on in my group.
Oh, cool.
But in any case, it would be really interesting to see this, to see if you could actually try to go all the way to the surface with these models. Would that be possible? If we, at least if we forget about the winds, so you try to do something like also, well, with you know, the Athena plus type of thing, but in your setting, would that, do you think, would be possible? To see if they survive?
No, unfortunately. So there's a few reasons. So one of them is that I wouldn't trust simultaneously resolving the core convection and the near surface convection just because of the very different aspect ratios of those convection zones. You would need to go to very high spherical harmonic degree to actually resolve the small scale features there. So that's one problem. Another problem is just that the density stratification tanks near the surface. And so I think we include like 11 density scale heights in this simulation, but there's many more in that near surface zone. And that is also extremely challenging.
Perhaps we could include it as a lower variable lower boundary.
Variable, or sorry, like what? Oh, you mean like put these waves in as a variable lower boundary? Yeah. I'm interested in doing that in the next few years, is like seeing how wave signals pass through something like a near surface convection zone and get modified. But yeah, I haven't actually thought about it more than like, that sounds fun.
Okay, so meanwhile, Dominic has cooled down 50 degrees, and he will answer why his fits are not complete grav.
I now know why chairs are important. Excellent, Evan, this is nice. Of course, a few years ago, we didn't have such fantastic simulations to compare to. So I'm very happy that we do have that now with this work. So just to re-emphasize what Connie says, these stars that we're looking at, these are rapid rotators, right?
Yes.
So periods of 10 days, I mean, that's slow for an O-type star, right?
It sure
so
is.
rotation is certainly important when interpreting the observed frequency spectra, and we do have fits that go down at low frequency.
Oh, cool.
So my question is, when we're looking at the transfer function,
it's one of these slides. This, or like
I think that the next one where you had
all of them.
Yeah, perfect. So yeah, I don't think we're that far off. And just to comment on Pablo's, I don't think it's two camps as you defined. I think there's the people who think it's subsurface, and then there's the people like myself who think it's both. And that's important to emphasize, right? Because I'm not saying the subsurface convection is negligible. I'm saying that we shouldn't ignore the waves excited by the core. Because they do have the characteristic shape, and with rotation, you can get a lot higher. But in your transfer function on the left here, am I understanding this correctly? That this is for all L's,
Yes.
Yeah.
Yeah.
Okay. Because
Or it's for L's 1 through 15, but yeah.
yeah, so this is interesting because, and I don't have a horse in this race.
Okay.
But for example, if I listen to someone like Falk Herwig, he would say in his simulations the dominant power of the waves are at L equals 30. But that doesn't seem to be what you're finding in your simulations. Have you looked into that?
So I can say that if you look at like the spectrum, we do get more power at higher L's at a fixed frequency. But when we account for cancellation effects, so when you just look at a hemisphere, like that is where that power disappears.
So how are you doing that cancellation? Because again, in Falk's paper, we had a look at this,
Yeah.
and the cancellation, the geometric cancellation, occurs when you have a coherent oscillation because of the limb
Right,
cancelling and incoming and outcoming
So
motion.
we're assuming coherency.
Yeah, so
Yeah.
in Falk's paper, we had a look at that, and because these waves are traveling waves, they're not coherent, it's not necessarily the case that there is coherency from one edge of the limb to the other. And then you can get quite considerable amplitude at the surface for high L.
Right. Our waves are fairly coherent in our simulations, and that's one thing that's really different between ours and Falk's. So that's something where like we need to get all of us in the same room and figure out what's going on.
Yeah, it'd be very good to work out why that is the case.
Yeah.
Because I'm not a numericist, and I'd like to understand that.
Yeah, we do use extremely different methods. So I am not sure what of those differences is the reason why we're seeing really different wave properties.
Excellent, thanks. Keep going.
Thanks, Tom.
Okay, I think we can close here. So if anyone has any further questions, I'm sure we can grab Evan in the coffee room or something.
Absolutely.
So let's thank Evan again. Thank you very much.